Okay, so we'll get right into action because we were in the middle of this lecture already, and there's just like a few slides left to get it done and move on to the SRAM lecture. We discussed the generic architecture for memories without getting into a specific memory technology. All of these are applicable to most memories that we will ever encounter in this course. So here's where we begin today. Floor plan. As the name suggests, is basically like, imagine you have a room and you are just going to fill it out with furnitures and other stuffs. You just plan it properly. Like, where would it be best to put the bed, and where can I put the table? Where can I put the chair? It's not just, yes, for there, that's an aesthetic choice, but for memory design, it's more of a performance choice. And here is why. So imagine you have memory controllers, you have processing units, you have, data cache, you have some other controller, and so on. All of these things are distributed in a 2D plane. Just keep that in mind. We have to deal with a two-dimensional area to distribute all of these components, right? Now, once you have this data cache here, you have to use these controllers to bring this data all the way to maybe this control units or processing unit. So there is a physical movement associated with memory read and write. Right? When you decide to fetch data, unlike in software, like when you see this virtual data movement, you don't see any physical movement. But practically, there will be a data movement from one physical location to maybe another, maybe somewhere else. I don't know. I'm just randomly picking them up, right? My point is, that's why this physical distribution matters. And I'll explain the extent to which it matters towards the end of this lecture, okay? Like today. Hopefully you'll see, we'll get back to this. But remember, how far the memory is from the processor, that actually matters. And that shows up in performance numbers. So if, long story short, if the memory is too far out from processor, you lose out performance. So you want it to be as close as possible. But you cannot put everything close to the processor, you see, because you have limited real estate. So you have to put some of them farther out. So how do you do it best? So different companies have their different architecture, obviously. So depending on who can manage to do it best will have better performance. And in this domain, you see like what a benchmark can do. I don't know if you guys are following news. Simply because a tool has a better benchmark versus some other company, all on a sudden you lose trillions of dollars of market equity, right? So just having a better benchmark could lead to disaster or huge advantage, as you can see. So all these companies fight for making the best floor plan so that, they have slightly better performance versus their competitors. They might all be using DRAM. Maybe all of them are using SRAM. But even with SRAM and DRAM, there is a distribution in performance numbers based on better floor planning. We'll get to the floor planning in the next slide as well. Look at this. Floor planning is not just limited to one small chip and distributing different smaller components within that chip. It is also on a larger scale. This is Google's floor planning. I typically make the students do it, but if you have computer open, you can Google how much energy it takes to Google, right? Or you can do it at home. So basically, there is an energy number associated with Googling anything. So every Google search takes a certain amount of energy. You might be wondering why, and that's a very big amount. I was given an analogy, something comparable to a light bulb running for a certain amount of time. Just one search. Okay, now imagine billions of people searching in a given minute all around the world. So that's like an energy burner like nothing. Just Google it. You don't have to trust me with this. So here is why the energy is associated with it. When you search something, Google has to access its data center. And its data center is not like it's a small chip, right? It's a room, basically. It's like a container, by the way, shipping container. This is essentially a shipping container that you're looking at. And within that shipping container, there are racks of storage components. And within these components, there are tiny storage devices. It could be SRAM, DRAM, flash, we don't know, depending on what Google decides to do with it. So when you search something, you have to first go to a container. Which container it is? Like there will be thousands of containers. And then within that container, you have to go to a rack. Within that rack, you have to go to a row. Within that row, then there has to be rows and columns for the actual memory array. So there is a huge selection process going on simply to return some cat images that you're searching. I don't know. Does that make sense? Okay, so floor planning could be as, seemingly insignificant as the first slide that you saw, to all the way to a data center that is so huge. So everything matters. Like floor planning definitely matters. So that brings me to a different context here. You must be seeing that I'm talking about a lot of architecture and high level stuff and trying to stay superficial without going into too much technical detail, because that's deliberate. I want to show you where the core interest of this course lies. Okay, and that brings me to the design hierarchy. In any kind of chip design related courses that you take, you have to deal with this hierarchy. We divide them up into 4 major levels: material, devices, circuits, and eventually systems. So for memory design related stuff as well, we deal with some materials that lead to designing memories. For example, spintronic materials, ferroelectrics, phase change materials. These are all materials that could be used to make memories. So you could either be a material scientist and still work on memory design. Essentially, you're a material scientist or a chemist, for example, but you work on memory. How is that possible? Because you use materials to make these memories. Okay, and these are all placeholder examples. Don't take them too seriously. Okay, I'm not going to go through them. These are just example of some fancy materials that looked cool. That's all. So you have materials, and then you use these materials to make devices. You basically bring multiple materials together. Like in the last iteration, what you are looking at is a phase transition material, in short PTM. So you connect that material with some transistor structure, you get a different device. So multiple material samples could come together to create devices. And the devices are as simple as a diode to BJT to MOSFET to more complicated devices. Okay, all of these fall under the category of devices, where you're looking at one small entity that could be used to store one bit of information. But remember, a device cannot work alone. You must have seen the architecture of memory. You need decoder, encoder, sense amplifier. You'll not use a sense amplifier for just one cell. That's completely impractical, right? You'll have an array of cells, rows and columns. How many of you remember the discussion? We use one decoder to choose the row, one decoder to choose the column. So if you have just one cell, you cannot do anything with one cell. So basically, as long as you're just dealing with one cell, you are dealing with the device, but you still have to go to the next level to do anything practical. That doesn't mean the device level research doesn't have impact. Basically, that's the most critical thing. You know why? I told you the answer in the last class. Memory is uniform. Whatever you do to the one device will be done to all the other devices. So you optimize and design the device like to the fullest extent that you can. And then once you make sure this is the best possible spintronic device that I can make in this technology, best possible ferroelectric that I can possibly handle, there you go. You have one cell. Then you just repeat that device over to arrays and you have your memory array. And then you do the other architecture stuff. So definitely device level research requires a lot of attention. But you must have seen, you cannot live without circuits. There will have to be so many different kind of circuits to sense what you're storing, to actually control what you're going to program, to access the data, to address the memory. So all of these are peripheral circuits. Okay, so there will be a lot of circuit. This is an example of a sense amplifier circuit. We'll have a separate lecture on this, don't worry. So there you go. You need to learn about circuits that are specifically related to memory. They're not general purpose circuits, but they're related to memory. And eventually, this is what we have seen already. You have to get to the system level where you have all of them coming together. That's where the architecture comes in. And architecture level innovation is a very different thing. You basically deal with individual components and you don't go into the depth of it. You just live with the edges, the pins that the underlying chips give you. I mean, am I making sense? All right. So these are the design hierarchy. Now, question is, where will this course focus on? I will tell you my logical answer. Devices. Here is why. That's where most of the R&D, research and development, is going on right now. Because most of the circuits, they work, don't change it, fine. They're based on standard transistors. You don't bring too many fancy materials or fancy technologies in designing or redesigning circuits. They're pretty standard. All of the examples that I gave you, like in the very first class, you use DNA to make memory. You use crystals to make memories, ferroelectrics, spintronics, memristors, blah, 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 right? All of these are what? Can you imagine? These are all pointing to devices. In fact, they're at the material device interface. So you use fancy material, you use that fancy material to make a device, and that device could be a memory device. Okay, so the core interest of this course will be here at this interface, because that's where most of the new concepts are. But then I also will touch upon the device circuit interface a little bit, and I will not be able to do much or practically anything with the architecture, because that's a whole different beast. Okay, that's actually at the edge of computer science more, and a little bit computer engineering, more into computer science, because that has to be closely designed with algorithm. What are you trying to do with this, right? So algorithm versus computer hardware design. So that's what you can expect. A lot of activities at the device material interface, some activities at the device circuit interface, and almost none at the system interface. Any questions so far? Sorry. Any questions so far? No? Okay. All right. That brings me to this really important concept that you need to understand. Everyone in this room should understand this. If you are to do anything on memory design moving forward, you should be aware of this so-called performance gap, or also known as memory wall. This is a problem that is driving a lot of innovation in our industries now. Basically, this is more like a driving force of multi-million-dollar proposals to trillion-dollar in industry investments and whatnot. Here is the problem. Can anybody take a look at this graph and help me make sense of it? So in the x-axis, we have years. Of course, super easy. In the y-axis, we have performance. And we are obviously talking about performance of something. And we have two graphs, one for the processor, one for the memory. You can clearly see the performance of the processor is going up, which is good. The performance of the memory is also going up. Like, yeah, which is good. Can anybody notice the difference here? And I have to tell you, what do I mean by performance? This is taken from a reference, so I didn't have any control over it. By performance, we mean speed. For this purpose, not energy, just speed. How fast these things can operate. So processors are getting faster. I don't have to tell you. Okay. Similarly, memories are also getting faster. Can anybody notice a difference here? There is a significant difference between the performance of the memory compared to the processors. So we're improving both of them, but they're not being improved to the same extent. Why is that a problem? There was a time not too long ago, even 15, 20 years ago, even maybe 15 years ago, when processors used to be, not that fast, honestly. They used to be sluggish. And we used to always have the memory sent you the data. The data is always ready. The processor finished computation and the next one was ready. So it took so much time for the processors to finish processing. Okay. So the clock, if you buy a Core i7 processor today, you look at some gigahertz numbers. 5-10 years ago, that number was much lower. In fact, at some point it was in megahertz region. So the processors were slower. The memory was not a problem in terms of speed. So people focused all of their energies, all of them, into making the processors better. Let's see what we can do to make them better. So they overdid it, as you see. Now the processors are so good, and I'll explain this later on, but this is not a processor course, but we'll still do that. In general, they did really well. They hit it out of the park. But nobody cared too much about memories. They are not our problem. But you don't address a problem until it becomes a problem. Now it has become a problem. You see why you should care now? Because now, moving forward, all the engineering energy will go where? Making the processors even better? I don't think so. They will have to. And here is why. Now, quite literally, this is what's happening. Your processors are done. And they're literally waiting on the next set of data to come. So there is an idle period. If you see the architecture level diagrams, you can visibly see, oh, idle period between processing. So this is insane. So your processors are so fast, but the memories are not being able to keep up. Okay. And you cannot even use the memories to the full extent of their ability, because if you read them too frequently, there is a chance of accidental flipping. Am I making sense? And I tend to use a simple example there. Imagine you are using a ferroelectric memory. Ferroelectric material has domains, and the more you read, you basically create some disturbance, and the domains gradually relax. And by reading it too many times, you essentially risk destroying the stored data. So you have to read, let it relax a little bit, and then read again, let it relax a little bit, okay? And remember, nothing is free. Whenever there is a current flowing through an entity, think of something, starting from your tables and chairs, to your copper and gold, to your plastics, everything has a property, that is resistance, except for superconductors, but everything else has resistance. So don't worry about any other secondary, deeper down physics stuff. Very simple Ohm's law. If current flows through something, when you read or write something, you have to flow current through it. No option, no other option, right? So when current flows through something, and that something has resistance for sure, you create I square R. So resistive drop. And over time, I square R T. So you generate heat. And that heat is a problem. Maybe not for one device, two devices. Just imagine you have billions, right? Anything time billions look much bigger. You see that? Even if it's like 1 nanojoule, when you multiply it with 1 billion, it becomes 1 joule, which is a lot of energy, by the way. Am I making sense? So when you access the memories over and over again, you heat it up. And what happens then? Everything is made out of material. Everything, like there is, I mean, who said it? Was it Joker? Everything burns. Like, I don't know if you have watched the Joker movie, but there was a dialogue there, like everything burns. So I would say everything melts, basically. So that's quite literally on chip. If you access something too many times, it generates that much heat that it could literally melt the material. So you cannot, so you have to stop. So whatever you see here, the situation is much worse. Oh, what happened to this? Give me 1 second, okay? It's not letting me. All right, I think now it should work. Let's see. Yeah. So whatever you're looking at here, that's the best case scenario. The practical situation could be much worse than this. All right. So this is a simplistic representation of the problem. Speed of the processor is going up. Memory is also going up, but there is a lag. And interestingly, what's more problematic is that the gap between the processor and memory is increasing. It's basically almost doubling every few years. So that's a very, very big problem. This gap is known as the memory wall. It's like a jargon that like the industry folks use all the time. How can you solve it? Right? You see the problem here? Do you realize the problem? Okay. That brings me to this concept, compute in memory, which is a topic of, there will be a lecture on compute in memory if you have gone through the syllabus. There is a reason why we have to talk about it, because that's the solution. That's where we are headed. Okay. We don't have, most systems don't have it yet, but we will get there. So von Neumann architecture is something that we all use. Any kind of devices that you're carrying with you today in this room uses von Neumann architecture. Von Neumann was a professor at Princeton. He thought about this architecture. What do I mean by architecture? Okay, you'll have decoder, you'll have encoder, you'll have sense amplifier here, you'll organize the rows, you'll organize the column. This planning, this high-level planning is called architecture. Obviously, it's more complex than that. It's quite literally, let me just go back to this diagram. This is more like it, like even higher level architecture. Where will the controllers be? Where will the processing units be? All of these high level details that falls under the architecture, okay? So von Neumann basically designed the architecture that is at the core of all computing units today, even to this day, like 50, 60 years ago. So just imagine the impact that you have had. Like all computing devices that will ever be created over the next 50 years will use your idea, right? He was a genius for sure. So no doubt. So this is the concept. So his architecture used a separate memory block and a separate processor block. And then there was a data bus and some peripheral circuit. These are all simplified concepts, as you see. So using the peripheral circuit, we need to bring information from the memory to the data bus. and the data bus feeds that into the processor. The processor does some magic, like some sort of computation, AND or XOR, whatever Boolean algebra you want to do. And then you have to put it back to the memory, the result that you have to put it back, right? So you have to go to the data bus again, and the data bus tells the peripheral circuit, you need to write this into the memory. And then the peripheral circuit goes to the memory and programs it. As I explain it, it already sounds like a lot of work, don't you think? But interestingly, the processor was so slow that all of this was like instantaneous compared to the processor speed. So we never cared for several decades. The processor was so slow compared to the memory. But now it's quite opposite. Processors are done computing, but all these other, data transport takes a humongous amount of time now. I forgot the exact numbers. It's there in our research papers that we often cite. It's from Google. Google actually quoted the number. It's an unreasonably high percentage that they spend in terms of energy usage, overall energy that the Google data centers require. Most of the energy, or actually a lion's share of the energy, is spent moving data from one place to the other, not computing. Forget about computing, just to bring the data and then put it back. This transport takes a significant amount of energy, which is crazy, right? So a solution, what could be a solution? One solution, which is currently considered to be the most viable and most promising. Can anybody suggest a solution? Anyone? No? Well, we don't want to go back, right? Now, for example, you just imagine one thing. You have gotten used to having so fast cell phones that if I give you a slower one, you can notice, oh, this is significantly slower, less responsive than that other thing. You can notice that. There is no going back. I've gotten used to this. I remember like having a smartphone when you have to click and wait. Okay, now it worked. Like literally, because that used to use resistive touch screen. Now we use capacitive touch screens, like really responsive, real time, right? So we have gotten used to it. No going back, of course. Without going back, how can we keep moving forward? The best way would be to not transport data. Like go where the data is and compute there. Like don't bring the data and put it back in. So how can you do it? The best way to do so would be to have some computing capability. Obviously, we still need a processor, by the way. You cannot have a general purpose computing capability within the memories. Memories are designed to store information. They're not designed to process. Okay, but maybe some of these computing steps could be done within the memory. Pay attention to this reasoning because that's what matters. You know why? If you ever interview for a company that deals with memory, they will ask you this question and they'll try to see whether you really understand the principle. Because honestly, whatever circuit I teach you, they don't use it. Right? They have their more advanced proprietary design that they are not going to publish and let us know. Otherwise, they will lose their business, right? So whatever you know has no value to them. They will anyways teach you about their technology when you join. But they want to see whether you have the perspective. Do you really understand the problem? If you don't, like, okay, this is very difficult to teach, okay? So I'm trying to address, where will it make sense? I cannot just, if I could make a processor within the memory, we would have never used this architecture to begin with. Because processing takes a very different task versus storing. Am I making sense? Here is why. Storing has to deal with not changing. Just keep that in mind. You are not trying to change anything so easily because you have to store that information in a reliable way. But processors are designed to be super volatile, meaning they change super fast. They change super easily. So it's easy to change states in the processor part. It's very difficult to change state in the memory because memories are designed to be stable, robust, not change so easily. How can you achieve both? No. If you try to use memories as processors, good luck, right? It's completely different design. But you can automate, or you can basically bring some select computing features within the memory, including AND operation, XOR operation, NAND operation, like some small basic Boolean computation. Am I making any sense here? Okay. All right. So I'll give you a direct example of, you have to justify why doing this computation within memory will help me. There comes AI. How many of you have heard about, AI training, inference, right? Making decision. You'll be surprised to know that deeper down, the computing primitives that AI uses are very simple. You just multiply and add, mostly. Just multiply and add. And there is a name, MAC, multiply and accumulate, MAC operations, right? Sometimes people use MVM, matrix vector multiplication. Still the same. After you multiply, you add. That's all. So MAC operation. So you need a multiplier and you need an adder. Okay. I'm not gonna talk about them in detail because we have a different lecture. So if you could somehow incorporate add operation within the memory, just add operation. Okay. Nothing else. I don't care about NAND, NOR, blah, 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 other complex Boolean functions, just add. So you do billions to trillions of this computation for every AI task, training to inference. If you could do all billions of them within the memory, that will save a significant amount of energy and, of course, speed. Does that make sense to you guys? Okay. So there you go, one selling point, but there are many others. This is not the only one. There are many other selling points, which we will try to talk about a little bit. So this is called compute in memory. Within the memory, can you create some extra? And obviously that requires extra peripheral circuitry. You have to control, you have to blah, 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 program it appropriately. So with modified peripheral circuitry, can you do compute in memory? Notice your processor is still there. Data bus is still there. The only thing that changed is this modified peripheral circuit. So you are still pretty much using the von Neumann architecture, but you have modified it a little bit to make your memory more active and more, participating in computing process rather than what they used to do. Okay. All of these were like high level discussions. And now it's time for us to dig deeper and get to the weeds of things. So from starting this lecture onwards, we really talk about technical details, right? So I'm excited to get started with that part. I guess all okay so far? Any question? Okay, all right. First topic is static random access memory, or SRAM. And there will be two parts, basically. This is the part one. So we'll start with, I'm just gonna throw it out there right away, and then take a step back and talk about other stuff. This is how static random access memory, or SRAM, looks like. And the name, the reasoning behind it will be clear as we move on in the lecture. So this is how the SRAM looks like. Let's see, how many transistors are there? This is a transistor, 1, 2, 3, 4, 5, 6. Everyone in the room knows what a transistor is, I guess, right? So I'm not gonna talk about it to that degree, but still I'll talk about some basics that is necessary to understand some deeper concepts. So apologize in advance to 335 folks who just took my course and went through this simple concept, but they will be pretty quick, trust me. I'm not gonna go into the details of any of this. Just to make sure everybody is in the same page, right? I don't expect everybody to have a device course right before taking this course. All right, so 6 transistors, you can count. That's why the name 60. Why are we spelling it out in the name 60? Because there are other versions of SRAMs. You have 70, you have 80, you have 10T, you have 12T. There are different numbers of transistors. You might be, why? To add extra features, okay? So that's why. We'll talk about it in 1 or 2 slides later on. But 60 is the most prominent, like 90% of all SRAM activities would be with 60. There you go, okay? All right. Interestingly, this circuit looks zigzagged and complicated. It is not. This is the simplified representation of the circuit. How many of you in the room have heard about CMOS inverter? Yes, 335 folks for sure, some others as well, but I also see a decent number of people who haven't possibly heard about it or remember the concept. So that's the reason why I will have a few slides discussing what CMOS inverters are and some other basic stuff. So don't worry. Let's take a step back and talk about transistor and inverter, because I assume some of you will not have the background, okay? All right, so a transistor, I'm assuming that you have the basic knowledge, so I'm just gonna be very quick. And for transistor, I'm only gonna deal with MOSFET. And for 335, I already told you, we don't care about BJTs anymore in digital electronics that much, right? We don't even really care about MOSFETs anymore. We care about FinFET, very recently people have moved away from FinFET as well. So MOSFET is old to old, like grandfather type of stuff. Anyways, but the basic concept remains the same. You have a source terminal, you have a drain terminal, you have a gate. When you apply some voltage, either positive or negative, depending on the polarity of the MOSFET, if you say, imagine you have positive voltage, it creates a channel between the source and drain, and the electrons can flow from source and drain. When you remove that voltage from the gate, this channel gets broken and you no longer have current flow. So essentially, this is a switch which turns on when you apply a voltage to the gate and turns off when you take away the voltage. Am I making sense? So for a transistor, you have, again, three terminals: source, drain, gate. When you apply VGS, gate to source voltage, you create a channel which can flow current. All right, there are two kinds of transistors, NMOS and PMOS. So basically, your source and drain could be made of N-type and the body could be P-type. Or the exact opposite. Source and drain could be P-type and body could be N-type. Okay. And I hope the 335 folks remember what N plus, P plus mean, right? If you don't know that, this is okay. This course is not about that. So don't worry, don't bother. This slide is essentially taken from 335, just to give you a perspective. This is how the transistor looks like. But more importantly, what it does, we're getting there in the next slide. But before moving on, this is a real picture. The other ones were cartoons, right? This is a real picture of a transistor. This is how the source look like. This is how the drain look like. Source, drain, this is gate, and this is where you create the channel. Once you create the channel, your electrons can flow through the channel from source to drain and so on. And once you break the channel down, no electron flow. As simple as that. This is one version, 65 nanometer node. This is a more advanced version, 45 nanometer node. But essentially, you see the structure and the concept remains more or less the same. Okay. All right. Moving to the next one, we will talk about the current voltage property of a transistor, which is the most important thing, which is what we use basically to design circuits. Okay. So let's see. Change the color. So you have source, drain, and imagine this is the channel. And you apply a VGS, a gate voltage, to the transistor. I told you, when you apply gate voltage, you create a channel. But there is a minimum that you have to pay. It's kind of like there is a minimum entry fee of $5, kind of like that, okay? So there is a minimum voltage that you have to apply to create that channel. That minimum voltage is called the threshold voltage. So if you apply more than threshold voltage, then you create the channel, okay? So that's why VGS greater than V threshold. So after you create the channel, so that's the VG, gate voltage. But now you have to deal with the other two terminals, drain and source. Simply because you have a channel doesn't mean the electrons will flow through the channel. For example, simply because there is a bridge doesn't mean I have to cross the bridge. There has to be a justification. Maybe there is a coffee shop on the other side of the bridge, so I'll cross it and get a coffee, right? There has to be some sort of motivation. Similarly, when you apply a positive voltage to the drain terminal, electrons on the source side, electrons love positive voltage. It's like a coffee shop. So they will cross the bridge to get to the other side. So you have to motivate. So basically, when you apply VG, it just creates the environment. But then you have to apply VD to invite electrons to really flow. So they're independent. You can have VG without VD. If you can have VD without VG. But if both of them are not present, then there will be no flow for sure. Okay. All right. So now, so basically you look at VGS, gate to source voltage, and VDS, drain to source voltage. You apply both, then you get current. The more drain voltage you apply, the more current flows through. And that's what you see here in this graph. The more VDS you apply, the more current flows through. So notice that it's a linear, almost linear. But after a certain amount of time, there are some reasons why this channel starts pinching off. So the current doesn't increase that much, it saturates. And then at some point, it completely pinches off and the current becomes constant. I don't know why it's doing it today. For some reason, it's... Anyways. All right. Let me just start from here. So your ID, drain current versus VDS. When you apply VGS and VDS, your current increases with VDS gradually, linearly. But at some point, it starts tapering off and then saturates. And this saturation actually represents that you have a pinch off. This is an older concept, by the way. In modern day transistors, we don't have pinch off anymore. There are other physical reasons. But interestingly, the effect is the same. You see the same effect. So for all practical purposes, we will start with linear and then we will saturate. And you can just mention that looking at the shape of the IDVDS, right? Linear and then saturation. Simple. So I'm going to tell you, without even going through all this secondary stuff that we covered in 335, let's try to draw the ID versus VDS from scratch again, one more time. This will be significantly quicker. So when you have, we are assuming that we have a VGS. Without a VGS, no channel. So it doesn't matter how much VDS you apply, zero current. Okay. And it's not just any VGS. You have to have a VGS which is greater than the threshold voltage. That's necessary. Okay. So once you have that, with increased VDS, you have more ID. More VDS you apply, more ID you get. Make sense? Okay. At some point, they will saturate. All right. Now, what if I imagine this graph, the green one, was for a certain VGS. Now, if I apply more VGS, like VGS2, which is even higher than VGS1, then what? It's kind of like, what does VGS do? Just try to remember it this way. VGS creates the bridge. Think of VGS to be an investment that creates the bridge. If you invest more, you have a wider bridge. If you invest less, you have a narrower bridge. That's all. So if you apply more voltage to the gate, it creates a wider channel and you can have more current flowing through. So essentially, you'll have a situation like this where you have a linear mode and then it will saturate eventually, but all of these current levels will be higher than where you started. Does that make sense? And they will all come down to zero, because when you have zero VDS, like, okay, you have bridge, but there is no motivation. Why will I cross the bridge, right? So zero VDS means no motivation. So everybody will come down to zero. Simple. All right. Now, if you apply even higher VGS, like VGS3, which is even higher than VGS2, you have, I mean, you can imagine, right? Simple. This is ID versus VDS characteristics of a transistor. I'm definitely simplifying it. There are more pattern here that I'm kind of ignoring for this particular course. I don't want to spend too much time talking about this, right? All right, so you have an idea. These characteristics, I mean, is casually known as output characteristics. Output. ID VDS characteristics is called output characteristics. Here is why. Take a look at the transistor. This is gate, this is drain, and source. You're looking at the drain to source current, or drain current, basically, and then you're applying a voltage between the drain and source. So all of these are at the output terminal of the transistor, and input is just the gate. So you have no involvement of the input in the Y or X axis. That's why this characteristics is often referred to as output characteristics. Now let's talk about, this is the output characteristics. Just explained. So I don't have to go through this slide. Okay, I've just explained this. The more VGS you apply, the higher the current levels are. Take a look at it at home. Okay, next is the transfer characteristics, and I'm going to talk about that now. Think of a transistor. This is gate, drain, and source. I'm looking at the drain current here, and I will plot ID versus VGS. Imagine for a second that you have applied a really high VDS, like, I don't know, 1 volt. Say, you've applied a good enough VDS, but no VGS. Will you get any current? So basically, let me just draw it here. Drain, source. This is your gate, right? You have not applied any gate voltage, zero gate voltage, but you applied some sort of, you know, drain to source voltage, which is like 1 volt, maybe, plus, minus. Do you think there will be a current? Why not? There is no channel. Like, we haven't even invested in the channel. So there is no channel. Even if I want to get to that coffee shop on the other side of the river, I cannot go because there is no channel. right? Does that make sense? And by the way, I'll get back and correct myself if you already know the answer, because I hope 335 folks remember where I'm getting with this. But regardless, for all practical purposes, we could agree that there will be no current. So zero current to begin with. When will you get a current? I just told you the answer. There is a minimum voltage, which is the threshold voltage. So up to the threshold voltage, you have no current. And when you cross the threshold voltage, you start getting more current, basically. Simple. So the more voltage you apply, more current you get. Does that make sense, folks? And I could explain the reason behind this, exponential, IV, whatever, but I'm not getting into the detail of it or quadratic characteristics. Let's just ignore it for now. Just you have more current as you apply more VGS. And think of it in a simple way that more VGS means more investment to build the bridge. And the wider the bridge is, the more current that you get. So yeah, simple. Yeah, you could have asked me like, okay, this graph will do just fine. More VGS, more current. Why are you making it carved like this, right? There are more mathematics involved in it. Not getting into that. That's what I'm telling you. Let's just take it for a given, okay? For this course. My point is, you have to cross a threshold to start getting some current. Now, let's get back to this again and draw this for different VDS. Okay, let's see. So you have ID versus VGS, and this is your threshold voltage. And you applied a VDS, certain VDS, which is not zero, like some VDS. Even if it is a tiny little VDS, that's fine. As long as there is a VDS, meaning an encouragement for the electrons to go, they will still go if there is a channel. And there is only a channel after threshold. So that's what you get. But maybe this is VDS1. I'm going to do this. And say now you have, say, VDS2, which is greater than VDS1. What do you do now? You still have to cross the threshold, basically. And then, since you have more VDS, you don't change the bridge. The bridge is there. But more VDS meaning instead of having one coffee shop, now you have a coffee shop and a golf course that you can get for free. Like, okay, oh, wow, more motivation for me. So then you can get more current, obviously. So more VDS you apply, you have more encouragement to get to the other side. And you have essentially more current, as simple as that. Does that make sense to all of you? Okay, remember this. But it's almost given that below threshold, the current is like zero. And you guys all agreed to this, right? And that was the norm for most engineers for 25 to 30 years, almost, even more than that. Nobody cared about what happens below threshold. Does anybody remember from 335 where I'm heading now? Can anybody drop me a keyword? Thank you. Yes. So nobody cared to look below the threshold. This is zero. Ignore it. But remember, there is always going to be some current. Even if there is no bridge, right? There are some motivated people who will just swim and get to the other side. How many of those people are there? Can you imagine? Only a few, right? If there is a bridge, maybe I will also cross. But if there is no bridge, I'm no swimmer. But there are swimmers. So even if there is no bridge or channel in a MOSFET, electrons can still go from one place to the other. There are processes, physical quantum mechanical processes called tunneling, and other secondary processes that could lead to current, even when there is no channel. But the current is so insignificant, so low compared to the actual current when the channel opens up, that people used to ignore it for the longest time. And I'll tell you the good reason. Here is what. Let me just ignore all of them, clear all of them. ID versus VGS. When you have the full potential of the transistor, when it fully turns on, this is called on current. And the on current is about, say, 100 microamps, 100 microamps. It's taking a number here. Below it, we used to take it as zero, but if you carefully measure, this would be, say, 1 nanoampere. 1 nanoampere, for example, okay? You know the difference between nano and micro? So what is the difference between these two levels? 10 raised to 5. Just divide them with each other. So 5 orders of magnitude. It's not like 10x lower, not 100x lower, not 1000x lower, not 10,000x lower. It's 100,000x lower. Like, who would care about a current that is 100,000 times lower than my own current? Nobody cares. Yes. And did I tell you about the power of big numbers? Especially in our era, instead of kilobytes, we deal with gigabytes and terabytes. And here is what. Ready for it? Okay. How many transistors will an SRAM have? How many? You just saw it. 6. I'll simplify it for you. Instead of 6, let's consider we have just one transistor. One transistor, okay? Just one transistor. Okay. Now, in a gigabyte, what is giga? 10 raised to? What is giga? 10 raised to 9. What is nano? 10 raised to minus 10. I just told you, instead of 6, I'm going to give you one transistor. That's the lowest you can get, right? So one transistor, every one of those transistors is leaking 1 nanoampere, even when there is no VGS. I haven't even turned on the transistor, it's off. But there will be a current. What is that current? 1 nanoampere. How many do you have? If you have a gigabyte sized, a gigabyte is nothing now, right? What is the storage of today's iPhone? Like, I don't know, 256 easily, 128. I don't know whether they sell a 128 anymore, but everybody starts with 256 typically, 512 gigabytes. But I'm going to take 1 gigabyte, which is nothing, not even a flash drive nowadays, right? Okay, 1 gigabyte is 10 raised to 9. And each one of those transistors are leaking 10 raised to minus 9. What is the total leakage every second? 10 raised to minus 9 times 10 raised to 9. This was ampere, by the way, nanoampere. So 1 ampere. And by the way, leakage is forever. Like, you are not applying any voltage, but it's leaking. You're not turning on the transistor by applying a gate voltage. It's leaking. Now, consider that for a second. Let me just put it into context. Have anybody looked at the battery size of iPhone? Some milliampere hour. Have you seen that? I don't know. Like, okay, I'm going to take some numbers. 4200 milliamp hour. It's like very high end. Okay. This is basically 4.2 ampere hour. Right? 4.2 ampere. So now do you see where 1 ampere is? Right? This is crazy. Like, if you just live with it, you cannot even, like, you will always be hooked up to the wall charging your stuff. So what can you do? So that's where, by the way, that brings me to this slide again. Oh my goodness. We are already over. I'm so sorry. I didn't realize we were already over time. So sorry, I'll stop here. And we will pick it up in the next class, okay? I mean, like I said, time flies. All right. Pick it up from the next class.